When we look up at the sun, we tend to see a perfect sphere of fire, steady, unchanging, a blazing engine that has burned for billions of years. But the truth, as every solar physicist knows, is far stranger and far more dynamic. I'm Michio Kaku, and today we're stepping into one of the most perplexing mysteries of modern solar science, a mystery that has challenged our theories for decades, resisting every attempt to make sense of it. It begins with a kind of cosmic rain. Not rain made of water, of course, but rain made of falling plasma, superheated, electrically charged gas, dropping down from the sun's outer atmosphere, the corona, like strands of glowing fire. We call it coronal rain. It is one of the most dramatic things we've ever observed on our star. But its beauty conceals a stubborn scientific puzzle. For years, we could see the rain. We could measure it. We could watch it cascade down magnetic loops with an elegance that seemed almost choreographed, but we could not explain it. According to our models, the very models that describe how plasma behaves under extreme temperatures, this rain shouldn't form for hours, sometimes days, after a major solar flare. Yet our telescopes, from powerful ground-based observatories to NASA's Solar Dynamics Observatory in space, kept recording the same thing. The rain appeared within minutes. How can something that should take hours happen in minutes? That question became a thorn in the side of solar physics. And once you tug on a thread like that, once you find something your theory cannot explain, you're forced to confront a deeper truth. Somewhere in the theory, something is missing. The mystery persisted partly because the corona is so hot, over 1 million degrees Celsius, that cooling it at all should be incredibly slow. So how could plasma cool fast enough to collapse, condense, and fall like rain? For decades, no one had an answer. And then two researchers, Luc Bonavita and Jeffrey Reep, decided to challenge one of the assumptions everyone had taken for granted. Their insight, as it turns out, was astonishingly simple. And like many breakthroughs in science, it hinged on a single elegant question. What if the corona's chemical composition is not constant during a flare? It sounds almost trivial, but this assumption that the corona's elements remain the same before, during, and after a flare was the foundation of almost every solar cooling model we had. No one had seriously questioned it because why would it change? But Bonavita and Reep had a suspicion. During a flare, the sun behaves like a boiling cauldron. Hot plasma erupts upward from the lower atmosphere, the chromosphere, in a process we call chromospheric evaporation. When this happens, the plasma isn't just hotter, it carries a different mix of elements. Elements like iron, magnesium, and silicon, what we call low FIP elements, meaning they have a low first ionization potential, get dragged upward in huge quantities. Now, why does that matter? Because these low FIP elements are incredibly efficient at one thing: radiative cooling. In other words, they help the plasma shed energy much faster than usual, and that means the corona can cool dramatically faster than any earlier model predicted. Like a switch being flipped, condensation begins. Suddenly, the impossible becomes inevitable. This was the breakthrough. When the researchers simulated flare loops with dynamically changing elemental abundances, allowing the concentration of iron and other low FIP elements to spike during a flare, everything fell into place. The cooling time plunged, the condensation formed, and the solar rain fell exactly when telescopes observed it, within minutes. For the first time in decades, the theory matched reality. To understand how significant this is, imagine trying to predict the weather on Earth while ignoring changes in humidity. The physics might look simple on paper, but the results would be hopelessly wrong. That's essentially what earlier models were doing. They treated the sun's chemistry as fixed, even as flares violently reshaped that chemistry in real time. And once you include that missing ingredient, once you allow the corona to change its elemental makeup dynamically, the entire picture transforms. This breakthrough does more than explain coronal rain. It rewrites a core assumption in flare physics. The corona's cooling is not slow because of temperature alone. It is governed by chemistry, by the balance of elements racing through magnetic loops, by the proportion of iron that suddenly surges upward like a tide, by the interplay between heat, plasma flows, and elemental abundance. We used to think of the sun's corona as an oven whose temperature was set by energy from below. Now we're discovering that the composition of the oven itself changes in the middle of the process. That changes everything. Because cooling is the key to understanding heating. We cannot peer directly into the heart of a flare's energy release, but we can watch how the plasma cools afterward. That cooling curve is like a fingerprint, a signature that tells us how energy was stored, released, and transported. If that fingerprint has been misread for decades, it means much of our interpretation of flare energetics may need to be revisited. The discovery also brings unity to several ideas in solar physics. For years, astronomers have observed that low phi-p elements are enriched in the corona compared to the photosphere. We call this the FIP effect. They've also observed that flare-driven flows lift enriched plasma upward. And they've observed runaway condensation, the point where radiative cooling overwhelms heating, causing plasma to collapse. But until now, these were pieces of a puzzle scattered across decades of research. Bonavita and Reap showed they are not separate pieces at all. They are part of a single coherent mechanism. It's a revelation that turns the once inexplicable into the beautifully obvious. As we examine this breakthrough, one theme becomes impossible to ignore. The sun is not a static machine. It is a living, breathing star whose chemistry dances in response to magnetic violence. And when that chemistry changes, the physics changes with it. The corona becomes a theater of dynamic transformation, shaped not just by temperature and magnetism, but by elemental flux. And that brings us to the question that now hovers over the field. If the corona's composition changes this rapidly during a flare, what else about flare physics must we rethink? We are standing on the edge of a paradigm shift. This is not merely an adjustment to theory, this is a redefinition of how flare models must be built. Radiative loss functions, which determine how energy escapes from plasma, must now incorporate composition that evolves minute by minute. Cooling curves must be recalculated. Simulations of flare loops, coronal heating, and magnetic reconnection must be rebuilt from the ground up. We are not just updating equations. We are rewriting the blueprint of solar flare physics itself. And this is only the beginning. To understand how transformative this discovery truly is, we need to step deeper into the physics. Because when the elemental composition of the corona shifts, everything downstream shifts with it. It changes how energy is radiated, how magnetic structures evolve, and how the sun's atmosphere reorganizes itself after a flare. And if we want to forecast space weather to protect satellites, astronauts, and power grids on Earth, this understanding is not optional. It is essential. Let's begin with the heart of the matter, energy. A solar flare is the explosive release of magnetic energy stored in tangled fields above the sun's surface. In a matter of seconds, that energy can equal millions of nuclear bombs. But the flare is only the beginning of the story. Once the magnetic field restructures, the heated plasma must cool and settle. It is during this cooling phase that the corona reveals its secrets. For decades, we believe the cooling process was governed almost entirely by two factors, conduction and radiation. Conduction transports heat along magnetic field lines, while radiation allows plasma to emit energy away as light. The equations describing this process seemed solid until we compared them with the sky, and that comparison failed. This is where elemental abundances come in. When iron and other low-FIP elements surge into the corona, the plasma becomes dramatically more efficient at radiating energy. It's almost like suddenly filling the atmosphere with millions of tiny radiators. The more iron you have, the faster the plasma cools. And the faster it cools, the sooner it collapses into rain. This dynamic abundance model doesn't just fix the timing problem. It recasts coronal rain as a natural, unavoidable consequence of flare-driven chemistry. It means the sun's atmosphere is not simply heating and cooling, it is chemically evolving in real time. This has profound implications. First, it changes our understanding of how flare loops behave. These loops, giant arches of magnetic fields stretching across tens of thousands of kilometers, act like massive pipes that conduct heat. Previously, we simulated these loops with fixed abundances. But if those abundances spike during a flare, then the entire thermal evolution of the loop must be recalculated. The peaks, the slopes, the cooling curves, all must be revisited. It's similar to rewriting the climate model of Earth after discovering that the atmosphere's composition changes every time a storm hits. Second, this discovery alters our interpretation of flare energetics. When we observe a flare, we cannot see the energy directly. We must infer it from what we can measure: temperatures, cooling rates, emission lines. If the elemental makeup of the plasma shifts, these emission lines shift with it. We have been reading fingerprints without realizing the ink was changing colors. This is why the discovery is so important. It prevents us from misinterpreting the sun's behavior. It prevents us from overestimating or underestimating the energy released in flares, errors that cascade into space weather forecasts. And third, the chemistry change influences structural evolution. When cooling accelerates, magnetic loops shrink more rapidly. Plasma drains faster, creating the spectacular cascade of bright falling strands we call rain. Observations have always shown this loop shrinkage to be rapid and dynamic. Now we understand why. But perhaps the most exciting implication is this: if the sun behaves this way, then other stars almost certainly do as well. Many stars across the galaxy experience massive flares, far larger than anything our sun produces. We see rain-like events on these stars too. If dynamic abundances govern cooling here, it is likely a universal mechanism operating across stellar atmospheres. That means this discovery affects not just the sun, but the stars that shape planetary systems throughout the Milky Way. But let's return to Earth for a moment. Space weather prediction relies on understanding what happens during and after a flare. When the corona cools more quickly, it changes how coronal mass ejections evolve. These ejections, vast clouds of charged particles hurled into space, can slam into Earth, damaging satellites, frying electronics, and causing power outages. During the Quebec blackout of 1989, for example, an intense solar storm shut down an entire power grid. Better cooling models mean better reconstructions of flare timing, energy release, and subsequent ejection behavior. They mean more accurate warnings for power companies, for astronauts on the International Space Station, for spacecraft navigating the harsh environment around Earth. The more accurately we predict these events, the safer our technological world becomes. Now, how do we actually observe these abundance changes? This is where modern solar missions shine. NASA's Solar Dynamics Observatory has given us unprecedented views of the solar atmosphere. The Solar Orbiter mission, led by the European Space Agency with strong NASA collaboration, is capable of measuring elemental abundances during flares in real time. And the Parker Solar Probe, humanity's first spacecraft to touch the sun, can directly sample the solar wind, giving us clues about how elemental signatures evolve as plasma escapes the corona. Together, these missions form a scientific triangle: imaging, spectroscopy, and in situ sampling. They allow us to test dynamic abundance models with extraordinary precision, and early data is already pointing in the same direction. The composition of the corona is not fixed. It evolves, it shifts, it breathes with the flare. This is a reminder that the sun is not a static ball of gas. It is an engine of physics, a laboratory where magnetism, plasma, and chemistry collide in ways that challenge our understanding. Every flare is an experiment. Every rain event is a clue. And when we combine these clues, a picture begins to emerge. Coronal rain is not a curiosity. It is a diagnostic tool. It tells us how quickly the corona is cooling, how much energy is being lost, how plasma is redistributed, and now, with dynamic abundance models, it also tells us how the corona's chemistry transforms in the minutes after a flare. This brings us to a deeper scientific question, one that strikes at the heart of solar physics. If elemental abundances change during flares, how far do those changes propagate? Do they remain confined to a single loop? Do they spread across active regions? Do they mix into the solar wind, altering what eventually reaches Earth? These are not small questions. Their answers could reshape our understanding of solar cycles, magnetic field evolution, and even the long-term behavior of the heliosphere, the enormous bubble of magnetic influence generated by our Sun. We stand on the threshold of these discoveries, and the breakthrough that started with coronal rain is now branching into dozens of new investigations across the globe. But the story doesn't end here, because with every major scientific breakthrough comes an even bigger challenge. What do we do with this new knowledge? That is where we turn next. As we step into this final chapter, we arrive at the question every breakthrough inevitably leads us to: now that we understand the missing piece of the puzzle, how does it change the path forward? What does this discovery mean for the next decade of solar science and for life here on Earth? To answer that, we need to consider how science progresses. Every great leap begins with a refinement, a correction, a moment when the universe taps us on the shoulder and whispers, "Look again." Dynamic elemental abundances are exactly that whisper, a reminder that the Sun is more intricate, more alive than we dared to imagine. And with that realization comes new responsibility, because the Sun is not merely the heart of our solar system. It is a force that shapes our technology, our communications, our power grids, even the safety of astronauts who drift through its electromagnetic breath. The clearer our understanding, the better we can prepare. One of the first consequences of this discovery is that it forces us to rebuild our models of coronal heating. For years, scientists have struggled to explain why the corona is so much hotter than the solar surface below it. Many hypotheses exist: magnetic reconnection, wave heating, turbulent dissipation, but each relies on accurate cooling measurements to infer how much energy is being pumped into the corona. If cooling models were incomplete, then the heating models built upon them become unstable towers of inference. Dynamic abundances stabilize those towers. They give us a more truthful reading of energy balance, one that reflects the Sun as it actually behaves, not as we once assumed it behaved. And then there is the practical side, forecasting space weather. Imagine trying to predict hurricanes without understanding how warm ocean currents fuel them. That is what forecasting solar storms has been like, working with incomplete physics. With this breakthrough, we're closer than ever to predicting when flares will intensify, how quickly plasma will cool, and how subsequent ejections will unfold. If we can refine those predictions, even by minutes, it could mean the difference between safeguarding satellites or losing them, between astronauts sheltering in protected modules or being exposed to dangerous radiation. Every fraction of accuracy counts. This discovery also sharpens our spectral diagnostics, the tools we use to decode the Sun's light. When elements like iron surge in concentration, they leave fingerprints across the electromagnetic spectrum. But if we assume those fingerprints are constant, we misread the Sun's behavior. With dynamic abundance models, each spectral line becomes a messenger carrying more accurate information about temperature, density, motion, and energy release. The result is clearer insight into how magnetic fields twist, snap, and release their stored energy. And perhaps most fascinating of all is the way this discovery expands our perspective beyond our own Sun. Across the galaxy, countless stars unleash flares far more violent than anything our Sun generates. On many of them, astronomers have seen rain-like events cascading along magnetic loops. The same phenomenon, the same mystery. If dynamic abundances are shaping cooling on the Sun, they may shape cooling on those stars as well. That means we may now have a universal mechanism, a bridge that connects the behavior of stars across the Milky Way. Sometimes the smallest insight, the faintest correction, becomes a key that unlocks cosmic patterns. But science never ends with an answer. It begins with new questions. Now that we know abundances change, we must ask, how do they evolve minute by minute? How do they move through the corona? Do they cluster? Do they disperse? Do they leave lasting imprints on magnetic regions? Missions like Solar Orbiter and Parker Solar Probe are uniquely positioned to explore these questions. Solar Orbiter can track abundance shifts with unprecedented resolution. Parker Solar Probe can sample the solar wind at distances never achieved before. Each mission adds a new piece to a rapidly expanding portrait of the sun's chemistry. And as our instruments become more sensitive, the story of coronal rain becomes more than an explanation. It becomes a gateway, a new lens through which we view the sun's atmosphere, from the smallest loops to the scale of its global magnetic cycle. But perhaps the most profound part of this discovery is philosophical. It reminds us that the universe is subtle, that nature hides her secrets not only in the vastness of space, but in the details of chemistry, in the dance of particles rising and falling in a storm of magnetic fire. We assumed the corona was static because we wanted simplicity, but the sun does not owe us simplicity. It offers us reality, dynamic, evolving, magnificent, and now we see that reality more clearly than ever. As we close this journey, we return to the image that began it, rain falling from the sky of a star, not water, but plasma, not clouds, but magnetic loops, a rain that defies intuition, but not physics, a rain whose mystery endured for decades, until we realized we had been missing an element, literally. With dynamic abundances now woven into our models, the sun's atmosphere becomes a more understandable, more predictable, and more humanly meaningful place. We can forecast storms with greater confidence. We can interpret flares with greater accuracy, and we can appreciate with deeper wonder the complexity of the star that gives us life. I'm Michio Kaku, and this has been a look into one of the most elegant advancements in solar physics. The sun still has many mysteries left to share, but today, at least one of them has stepped into the light.